Good day, everyone. So let us continue our discussion on intelligent systems. Okay, so here's the outline of our discussion. We will define what is symbolic learning, overview of computer vision, what are the traditional methods in computer vision, AI in computer vision, neural networks in computer vision, deep learning for image recognition, and symbolic AI in computer vision. So basically, symbolic AI involves the use of logical rules and representations to solve complex problems. Okay? Symbolic AI uses logical rules and representations to solve complex problems. Unlike statistical approaches, it employs explicit representations of knowledge to reason and make decisions. For example, in computer vision, symbolic AI can be used to interpret scenes by analyzing shapes, relationships, and context. Okay, so that's symbolic AI. To further understand what symbolic AI is, let us watch the following videos.
Back in 1959, three AI pioneers set out to build a computer program that simulated how a human thinks to solve problems. Alan Newell was a psychologist who was interested in simulating how humans think, and Herbert Simon was an economist who later won the Nobel Prize for showing that humans aren't all that good at thinking. They teamed up with Cliff Shaw, who was a programmer at the Rand Corporation, to build a program called the General Problem Solver. To keep things simple, Newell, Simon, and Shaw decided it was best to think about the content of a problem separately from the problem-solving technique. And that's a really important insight. For example, my brain would use the same basic reasoning strategies to plan the best route to work, school, or wherever I need to go, no matter where I start. Computers are logical machines that use math to do calculations. So, logic was an obvious choice for the general problem solver's problem-solving technique. Representing the problem itself was less straightforward, but Newell, Simon, and Shaw wanted to simulate humans, and human brains are really good at recognizing objects in the world around us. So, in a computer program, they represented real-world objects as symbols. That's where the term symbolic AI comes from, and it's how certain AI systems make decisions, generate plans, and appear to think. Hey, I'm Jabril and welcome to Crash Course AI. If you've ever applied for a credit card, purchased auto insurance, or played a computer game newer than something like Pac-Man, then you've interacted with an AI system that uses symbolic AI. Modern neural networks train a model on lots of data and predict answers using best guesses and probabilities. But symbolic AI, or good old-fashioned AI, as it's sometimes called, is hugely different. Symbolic AI requires no training, no mass amounts of data, and no guesswork. It represents problems using symbols and then uses logic to search for solutions. So all we have to do is represent the entire universe we care about as symbols in a computer. No big deal. To recap, logic is our problem-solving technique, and symbols are how we're going to represent the problem in a computer. Now, symbols can be anything in the universe. Numbers, letters, words, bagels, donuts, toasters, John Greenbots, or Jabrils. One way we can visualize this is by writing symbols surrounded by parentheses, like donut or Jabril. A relation can be an adjective that describes a symbol, and we write it in front of the symbol that's in parentheses. So, for example, if we wanted to represent a chocolate donut, we can write that as chocolate donut. Relations can also be verbs that describe how symbols interact with other symbols. So, for example, I can eat a donut, which we will write as eat Jabril donut, because the relation describes how one symbol is related to the other. Or we can represent John Greenbot's relation to me using sidekick John Greenbot Jabril. A symbol can be a part of lots of relations depending on what we want our AI system to do. So we can write others like is John Greenbot robot or where's John Greenbot polo. All of our examples in this video will include a max of 2 symbols for simplicity, but you can have any number of symbols described by one relation. A simple way to remember the difference between symbols and relations is to think of symbols as nouns and relations as adjectives or verbs that describe how symbols play nicely together. This way of thinking thinking about symbols and their relations lets us capture pieces of our universe in a way that computers can understand. And then they can use their superior logic powers to help us solve problems. The collection of all true things about our universe is called a knowledge base, and we can use logic to carefully examine our knowledge bases in order to answer questions and discover new things with AI. This is basically how Siri works. Siri maintains a huge knowledge base of symbols. So when we ask her a question, she recognizes the nouns and verbs, turns the nouns into symbols and verbs into relations, and then looks for them in the knowledge base. Let's try an example of converting a sentence into symbols and relations, and then using logic to answer questions. Let's say John Greenbot drives a smelly old car. I could represent this statement in a computer with symbols John Greenbot and car, and then the relations drives, smelly, and old. Using logical connectives like and or, we can combine these symbols to make sentences called propositions. And then we can use a computer to figure out whether these propositions are true or not, using the rules of propositional logic and a tool called a truth table. Propositional logic is basically a fancy name for Boolean logic, which we covered in episode 3 of Crash Course Computer Science. And the truth table helps us decide what's true and what's not. So, in this example, if the car is actually smelly and actually old, and if John Greenbot actually drives the car, then the proposition smelly car and old car and John Greenbot drives the car is true. We can understand that sort of logic with our brains. If all three things are true, then the whole proposition is true. But for an AI to understand that, it needs to use some math. With a computer, we can think of a false relation as 0 and true relations as any number that's not 0. We can also think of ands as multiplication and ors as addition. But let's look at what's happening to the math if the car is not actually old. Again, our brains might be able to jump to the conclusion if one of the three things isn't true, then the whole proposition must be false. But to do the math like an AI would, we can translate this proposition as true times false times true, which is 1 times 0 times 1. That equals 0, which means the whole proposition is false. So that's the basics of how to solve propositions that involve and. But what if we want to know if John Greenbot drives a car and that the car is either smelly or old? Like I mentioned earlier, or can be translated as addition. So using our math rules, we can fill out this new, bigger truth table. The proposition we're dealing with now is smelly car or old car, and John Greenbot drives the car. For the first row, this translates as true plus true. Then that result times true, which we calculate as 1 plus 1 times 1. That equals 2 times 1, which is 2, which means the whole proposition is true. Remember, any answer that isn't 0 is true. The second row translates as true plus false. Then that result times true, which we calculate as 1 plus 0 times 1. That equals 1 times 1, which is 1, which means the whole proposition is true again. And we can fill out the rest of the truth table the same way. Another logical connective besides and or is not, which switches true things to false and false things to true. And there are a handful of other logical connectives that are based on ands, ors, and nots. One of the most important ones is called implication, which connects two different propositions. Basically, what it means is that if the left proposition is true, then the right proposition must also be true. Implications are also called if-then statements. We make thousands of tiny if-then decisions every hour. Like, for example, if tired, then take nap. Or, if hungry, then eat snacks. And modern symbolic AI systems can simulate billions of if-then statements every second. To understand implications, how about we use a new example? If I'm cold, then I wear a jacket. This is saying that if I'm definitely cold, then I must be wearing my jacket. But if I'm not cold, I can wear whatever I want. So, if cold is true and jacket is true, both sides of the implication are true. Even if I'm not cold and I wear my jacket, then the statement still holds up. Same if I'm not cold and I decide to not wear my jacket. I can do whatever I want since I'm not cold. But if I am cold and I decide not to wear my jacket, then the statement no longer works. The implication is false. Simply put, an implication is true if the then side is true or the if side is false. Using the basic rules of propositional logic, we can start building a knowledge base of all the propositions that are true about our universe. After that knowledge base is built, we can use symbolic AI to answer questions and discover new things. So for example, if I were to help John Greenbot start building a knowledge base, I told him a bunch of true propositions. Oh, John Greenbot. Alright, you ready, John Greenbot? So, Jabril is person. John Greenbot is machine. Car is machine. Car is old. Car is smelly. John Greenbot is not person. Jabril isn't machine. Toaster is machine. You getting all this, John Greenbot? Clearly, at this pace, John Greenbot would never be able to build a knowledge base with all the possible relations and symbols that exist in the universe. There are just too many. Fortunately, computers are really good at solving logic problems. So, if we populate a knowledge base with some propositions, then we can use a program to find new propositions that fit with the logic of the knowledge base without humans telling it every single one. This process of coming up with new propositions and checking whether they fit with the logic of a knowledge base is called inference. For example, the knowledge base of a grocery store might have a proposition that sandwich implies between meat, bread, or if sandwich, then between meat, bread. Meat and bread are the symbols, and between is the relation that defines them. So basically, this proposition is defining a sandwich as a symbol with meat between bread. Simple enough. There might be other rules in the grocery knowledge base, like for example, a hot dog also implies between meat bread, or if hot dog, then between meat bread. Now, if the grocery store is having a sale on sandwiches, should the hot dogs also be on sale? Well, with inference, the grocery store AI system can apply the following logic. Because sandwiches and hot dogs are both symbols that imply meat between bread, then hot dogs are inferred to be sandwiches, and the discount applies. Over the years, we've created knowledge bases for grocery stores, banks, insurance companies, and other industries to make important decisions. These AI systems are called expert systems because they basically replace an expert like an insurance agent or a loan officer. Symbolic AI expert systems have some advantages over other types of AI that we've talked about, like neural networks. First, a human expert can easily define and redefine the propositional logic in an expert system. If a bank wants to give out more loans, for example, they can change the propositions involving credit score or account balance rules in their AI knowledge base. If a grocery store decides they don't want to discount hot dogs during the sandwich sale, then they might redefine what it means to be a sandwich or a hot dog. Hey Siri, is a hot dog a sandwich?
Of course not, Jabril. Do not waste my time with foolish questions.
Second, expert systems can make conclusions based on logic and reason, not just trial and error guesses like a neural network. And third, an expert system can explain its decisions by showing which parts were evaluated as true or false. A symbolic AI can show a doctor why it chose one diagnosis over another, or explain why an auto loan was denied. The hidden layers of a neural network just can't do that. At least, not yet. This so-called good old-fashioned AI has been really helpful in situations where the rules are obvious and can be explicitly entered as symbols into a knowledge base. But this isn't always as easy as it sounds. How would you describe a hand-drawn number 2 as a symbol in a number knowledge base? It's not that easy. Plus, lots of scenarios are not just true or false. The real world is fuzzy and uncertain. As we grow up, our brains learn intuition about these fuzzy things, and this kind of human intuition is difficult or maybe even impossible to program with symbols and propositional logic. Finally, the universe is more than just a collection of symbols. The universe has time, and over time, facts change and actions have consequences. So next time, we'll talk about these actions and consequences, and how robots use symbolic AI to plan out their jobs and interact with the world. Until then, I'm gonna finish this sandwich. Crash Course AI is produced in association with...
Hello and welcome to this video on symbolic artificial intelligence. In this video, we'll be discussing what symbolic AI is, its history, and some examples of its applications. First, let's define what symbolic AI is. Symbolic AI is a subfield of artificial intelligence that focuses on using symbols, logic, and formal reasoning to represent and manipulate knowledge. It involves creating explicit, rule-based systems that can perform tasks such as problem-solving and decision-making. The history of symbolic AI can be traced back to the 1950s, when researchers first began exploring the idea of creating machines that could mimic human intelligence. Early efforts in the field focused on creating rule-based systems that could perform simple tasks, such as playing chess or solving mathematical problems. One of the key features of symbolic AI is that it uses a symbolic representation of knowledge. This means that information is represented as a set of symbols, such as words or numbers, and logical rules are used to manipulate and reason about this information. This approach is in contrast to other subfields of AI, such as machine learning, which uses data and statistical algorithms to learn from examples. One of the most well-known examples of symbolic AI is expert systems. These are computer programs that are designed to mimic the decision-making abilities of a human expert in a specific domain. For example, an expert system for diagnosing medical conditions would use a set of rules and a knowledge base of medical information to make a diagnosis. Another example of symbolic AI is natural language processing systems, which use formal grammars to understand and generate human language. These systems can be used for tasks such as language translation or text summarization. In recent years, the field of AI has shifted towards approaches that are more data-driven, such as machine learning. However, symbolic AI still plays an important role in many areas of AI, particularly in fields such as knowledge representation and reasoning. In conclusion, symbolic AI is a subfield of AI that focuses on using symbols, logic, and formal reasoning to represent and manipulate knowledge. It's an important area of research that has led to the development of many practical applications, such as expert systems and natural language processing systems.
Okay, so let's continue on the importance of AI symbolic learning in computer vision. So we have here 5 importance of AI in symbolic learning, okay, in computer vision. We have a semantic understanding, we have interpretability, knowledge integration, robustness, and explainability. When we say semantic understanding, okay, symbolic learning helps in understanding the semantics of visual content, okay, enabling them more accurate interpretation of images. So dito, iniintindi ng computer vision with the aid of AI yung visual content para nang sa ganun, makapagbigay siya ng mas accurate na interpretation ng images. Okay? So that's semantic understanding. The next one is interpretability. It provides interpretable representations of visual data, aiding in debugging and improving the transparency of computer vision systems. Okay, so that's interpretability. Provides interpretable representations of visual data. Okay, the third one, or the knowledge integration, it is the symbolic learning that allows integration of prior knowledge and domain expertise into computer vision models, enhancing their performance in specific tasks. So that's knowledge integration. The fourth one is robustness. No? By incorporating symbolic reasoning, no, computer vision systems can achieve greater robustness to noise, occlusions, and various variations in data. Okay, so that's robustness. The fifth one is explainability. When we say explainability, symbolic AI facilitates the explanation of decision-making process in computer vision algorithms, increasing trust and accountability in AI systems. So that's the importance of AI in computer vision: semantic learning, interpretability, knowledge integration, robustness, and explainability. To further understand the following concepts, let us watch these 3 videos.
Computer vision explained in 5 minutes. Hi, everybody. If you're looking to start your career as a computer vision professional from scratch, then you are in the right place. Computer vision, or CV, is a branch of computer science that empowers machines to see, recognize, and process images just like humans. Computer vision is, in fact, a multidisciplinary field. It could be called a subfield of artificial intelligence, AI, and machine learning, ML. Computer vision makes use of general learning algorithms and may require the use of specialized methods. This diagram shows the relationship between artificial intelligence and computer vision. Being a multidisciplinary field of study can seem messy for a beginner. The reason for this is some techniques are borrowed and reused from an assortment of engineering and computer science fields. Understanding the content of digital images is the main objective of computer vision. This might seem easy, but it's not so because computers are not the same as humans. They don't have the gift of vision and perception. While seeing and perceiving the world around them comes naturally to humans, that's not the case with computers. How do computer vision algorithms work? The computer vision algorithms used today are based on pattern recognition. They typically rely on convolutional neural networks, or CNNs. Computers are first trained on an enormous amount of visual data. In this step, computers process images and label the various objects on them. They also find patterns in those objects. For instance, if we send 1 million images of cats, the computer will first analyze all the images. It will then identify patterns that are similar to all cats, and at the end of the whole process, create a model cat. As a result, the computer can accurately detect whether or not a particular image is a cat each time we send it pictures. The unprecedented growth of computer vision. Images dominate the internet today. They are everywhere: social media, e-commerce stores, travel sites, and more. But along with an enormous amount of visual data, over 3 billion images are shared every day, we also have easy access to the computing power needed to analyze this data. Computer vision is a booming field due to the latest advancements in this field. It's true that the field of computer vision has grown exponentially in the last few years alone. New hardware and advanced algorithms have ensured that the accuracy rates for object identification are high. In less than a decade, the improvement in the accuracy percentage has been phenomenal. It's gone up from 50% to 99%, making today's systems more accurate than humans. It's an accepted fact that computers react much more quickly than humans to visual inputs. The applications of computer vision. The earliest experiments in computer vision began in the 1950s. Computer vision was, however, first put to commercial use only in the 1970s to differentiate typed text from handwritten text. But today, computer vision is a reliable and mature technology that generates huge cost savings and saves time, from defect detection to intruder detection, mask detection to tumor detection, crop monitoring to plant monitoring, vehicle classification to traffic flow analysis. And from customer tracking to theft detection, the applications of computer vision are truly varied. Computer vision is used extensively in the following fields: retail and manufacturing, transportation, insurance, media, agriculture, healthcare, sports, banking, augmented reality and mixed reality, home security, and content management and analysis. The most popular computer vision applications include object classification, recognizing the broad category of an object in a photograph; object identification, identifying the type of object in a photograph; object detection, detecting the location of an object in a photograph; object verification, verifying the presence of an object in a photograph; object landmark detection, detecting the key points for an object in a photograph; object segmentation, segmenting the pixels that belong to an object in an image; and object recognition, recognizing the objects in a photograph and pinpointing their location. Your path to computer vision mastery. We have an in-depth course on the AI Sciences platform that covers computer vision. We also have a short course on computer vision for beginners. Name of the course: Computer Vision Theory and Projects in Python for Beginners, 18 sections. You'll learn the core concepts of the computer vision field in this course. The important elements of this course are the 2 hands-on projects in the concluding section: change detection in CCTV cameras and smart DVRs. Name of the second course: Mastering Computer Vision, Theory and Projects in Python, 323 lessons. In this in-depth course, you'll learn to master the basic concepts of computer vision first. Next, you'll move onward to advanced concepts. If you're interested in learning more about becoming a computer vision professional, then be sure to check out our courses at the first link in the description. Subscribe and turn on notifications so you don't
In this short video, we will discuss what exactly computer vision is and some real-life examples of computer vision. Let's jump right in and talk about the definition of computer vision. Computer vision is a field within artificial intelligence. You might be familiar with the acronym AI, which is artificial intelligence. Well, computer vision is the same and is often seen written as CV. Computer vision uses algorithms to understand digital visual data in the same way the human eye does. Yes, that's right. Computer vision is when algorithms process visuals, hence the name. Computer vision models translate what they see into data, and from here, they can take meaningful actions or make recommendations based on the data they have seen. Think of it this way. Imagine you are walking through the jungle, unprepared and scared. There are snakes everywhere. You need to know which are venomous and which are harmless, but you haven't done any research and can't tell the difference between them all. Luckily for you, your friend gave you a super cool pair of what she called computer vision glasses right before you set off. You put them on, and as you look at the different snakes in front of you, you can now see the glasses are processing the view and detecting which snakes are venomous and which ones are not. That is computer vision. Now, we're not saying that these glasses are widely available for you to purchase, but it's a pretty cool idea and a very concrete way of illustrating what computer vision is. Now let's talk about computer vision in action. The rise of autonomous or self-driving cars is possible only due to computer vision techniques and technology. Cameras on these cars track its surroundings as well as detect and classify objects. Once this is done, this information is passed further on to the rest of the tech, which makes decisions based on this information. Another common example is translator apps. Think the Google Translator. When you point your phone camera at the words, it can almost instantly translate this into the language you have chosen. There are plenty more real-life applications of computer vision that we haven't discussed, but we would love to hear what examples you can think of in the comments below. As always, you can find more resources to this and other topics in the description box. Thanks for watching. Now that you're here, I wanted to tell you about Levity. Levity is a tool that allows you to train AI models on images, documents, and text data. You can rebuild manual workflows and connect everything to your existing systems without writing a single line of code. If you liked this video, you'll probably love Levity, and we can't wait to hear from you.
Okay, so let us continue on the concepts and principles of symbolic AI. We have here knowledge representation, inference, knowledge acquisition, and knowledge integration. Okay, so symbolic AI involves the representation of knowledge using logical symbols and rules, okay, to perform reasoning and problem-solving tasks. When we say knowledge representation, it is representing information, okay, using symbols, logical rules, facilitating reasoning. That's knowledge representation, okay? Inference naman is drawing logical conclusions from available knowledge using deductive, inductive, and abductive reasoning. Okay, that's inference. The third one is knowledge acquisition. Knowledge acquisition, okay, methods for acquiring knowledge from data, from experts or external sources to enrich the knowledge base, from the word acquisition, acquiring of knowledge from various sources. Okay. Last one is knowledge integration. When we say knowledge integration, integrating diverse sources of knowledge to build comprehensive models of the world. So, upon acquisition of knowledges, i-integrate naman na itong mga sources na to. Para nang sa ganun, it can build a better model of an idea of knowledge of the world. Okay, so those are the concepts and principles of symbolic AI: knowledge representation, inference, knowledge acquisition, and knowledge integration.